Today we're looking at the confidence intervals. So we define a confidence interval. That gives us the range of values which we have a certain level of confidence that the true mean of the population will fall. So generally when we have a sample, we don't have the true mean of the population, but we can use that information to come up with a confidence level that the true mean of the entire population will fall. So the formula we talked about for confidence intervals is the sample mean plus or minus the margin of error. Now this is our calculation to find the margin of error. Z star is the z-score associated with the confidence interval. And this is sigma, stands for standard deviation of the population, and the number of the sample. And then x bar is our sample mean. Now we have to figure out how to find that z star. And to find the z star, if we had a 90% confidence interval, we want this mean right in here. And that gives us a 90%, 0.90 probability right here that it's in there. So that leaves a 0.05 at this end and a 0.05 at that end. Because 1 minus the 0.9 gives those symmetric tails an area of 0.05. So this z star is this upper bound. So if this is 0.05 and this is 0.9, for this problem, z star is going to be that probability of 0.95. That's the area under the curve up to this z star. This is where we're looking for z star, 0.95. So how do we find a z-score given the area under the curve? If we're using our calculators, we have to do inverse norm. If we're using the chart, we go from the inside, work our way out to find that z-score. So if you're a chart person, you're looking inside the chart for 0.95. So I've got a chart in here somewhere. Let's see if we can find it. All right, so we're looking inside for 0.95. It's halfway in here, isn't it? So the z-score that corresponds to this would be 1.6, and it's halfway in between those two, so 1.645. Yeah, let's go back to our notes. We know that the z-score that's associated with a probability of 0.95 is approximately 1.645. Guys, if you do inverse norm of 0.95 with a standard deviation of with a mean of 0 and a standard deviation of 1, it gives you a number that would round to this exact same thing, wouldn't it? Okay, so that's how we find z star. That's the only thing we actually have to find. We're plugging the rest in. So how does this work? Example 1. A college admissions director wants to estimate the mean age of all students currently enrolled. In a random sample, well that's good, it's a random sample, that's one of our ideal sampling methods, of 20 students, well that's not as good, we want it to be at least 30. The mean age of the sample is 22.9 years. From past studies, the standard deviation is 1.5 years. Construct a 95% confidence interval of the population age. Okay, I'm very visual, and since we're just starting, I want to see the curve. 95%. So 0.95. I want the mean somewhere in there. So what is this z star right here?
0.02.
Okay, that's where I need to find it. Well, we know that this is 0.5. So this would be 0.025, right? 0.025 to make up the 1, the total area of 1 under the curve. So what is this area we're looking for here? It would represent a probability of 0.975. Okay, so if you're looking for a shortcut, some of us are always, actually not a shortcut, some of us are always looking for a pattern. Well, the pattern here to find the z star is if you take your confidence interval, whatever your confidence interval level is, in this case 95%, and you do 1 minus that, and then divide that by 2. That is what you just add back to your confidence interval level. So in this case, if we did 1 minus 0.95, divide that by 2, and add it back to 0.95, do you see that gives us the 0.975? Now some of us are visual, and it might help us to draw the curve. So whichever way you are. So we're looking for the z-score associated with a probability of 0.975. Okay, you can use your calculator and do inverse norm, or you can use a table. And let's round that to 2 decimal places.
You still need calculator.
Got it.
Okay, did you get 1.96?
Yes.
Cool. All right, so now we have everything we need. All right, the formula once again was X for the confidence interval. The formula that we're looking for is X bar, the mean of the sample, plus or minus the z-score associated with the level of confidence, the standard deviation of the population divided by the square root of n. So let's look for those things in this problem. Oh, there's the mean of the sample, 22.9, plus or minus z star we just determined was 1.96. The standard deviation is known to be 1.5, and we've got 20 here. Okay, so this is 22.9 plus or minus, if I type into my calculator, 1.96 times 1.5 divided by square root of 20. It gives me approximately 0.657. So this confidence interval looks like this. 22.9 minus the 0.657 gives us a lower bound of 22.243. 22.9 plus 0.657 gives us that upper bound of 23.557. Now, this is where we get into something that if you're in statistics, you know. The wording of our answers is really important, but a lot of times it ends up just being fill in the blanks. And our interpretation of a confidence interval is one of those things. So this is a fill in the blank kind of answer. Once we find this, we just fill in the blanks, and it goes something like this. We are blank % confident that the true mean of whatever our problem is talking about, so the true mean of blank, is between blank and blank. And then describe our units if necessary. So, this is what we'll fill in every time. In this problem, what is the confidence that we were looking for? A confidence level of 95%. So we are 95% confident that the true mean of what? What were we looking at in this problem? We were looking at the age of all students. The true mean age of all students is between our lower bound, which is 22.243, and our upper bound, which is 23.557. And what is our unit for these ages? Years of age. Yep. So these are just fill in the blank. Okay, now the last little example on your notes today deals mainly with just margin of error. And let's read this problem together so that we can, wow, there we go. A soccer ball manufacturer manufacturer wants to estimate the mean circumference of soccer balls within 0.1 of an inch. So this manufacturer will accept this much differentiation. This is our margin of error. This manufacturer is okay with that much variation. So the margin of error from our formula is equal to Z star times sigma over the square root of n. This says if the population standard deviation is 0.25, well, that's my sigma. Let's plug it in. Determine the number of soccer balls that are needed for a 99% confidence level. Okay, so they gave me the margin of error, 0.1. I should have filled that in earlier. I'm solving for n, but what I have to do is figure out the Z star. What is Z star associated with a confidence level of 99%? So, if my confidence level is 99, 0.99 right here in the middle, this is 0.05, this is 0.05, so what probability am I looking up? Yep, that is exactly what I mean. Thank you. Appreciate that. So, here we're looking up that probability of 0.995. Please find the Z-score associated with a probability of 0.995, which is a 99% confidence level. I used the calculator and I gave myself 3 decimal places. I am estimating my Z-score here, so I'm just going to change these to squiggles for approximately equal to. Did you get 2.576? Alright, and now we just have to solve for n, guys. So when we're solving this for n, we got to multiply by the square root of n to get it out of the denominator, and then divide by the 0.1. And what's the last step I have to do with all this? Square it. Let's see what you get. See if your answer matches mine. Okay, so this is what I got. Did you get the same thing? 41.516? Okay, I'll check yours in a second. So how many balls do they need to sample to assure 42? 42. We can't round down because that wouldn't take us all the way to a 99%. So we'd have to sample 42 balls to assure a 99% confidence level that all the balls were within 0.1 inch.
It's not that far, it's 4.474.
I got 4.722.
How often in these 4 times?
No, yours is right. Okay, so my work is wrong.
That's what I got too.
That's the first.
472?
473.
474? Okay. It would still be 42 balls. I rounded this to 6.44 and then squared that instead of, shame on me, I compounded my error.